Hi, I'm Mrs. Edwards, and today we're going to go over functions and their inverses. We're going to begin by looking at some graphs of a function and its inverse, and then we're also going to analyze a couple of points on the graph. This is a way that we can informally determine if two functions are inverses of one another. But eventually we're going to get to a more formal approach where we can prove this algebraically, and then we're going to do a few applications of inverses. Let's start here with g of x and h of x. I've already graphed both of these on the same graph paper. I did this at desmos.com. And a quick note about graphing. If I'm trying to graph the cube root of x minus 5 plus 1, notice that I have x minus 5 in parentheses, and the exponent on x minus 5, which is kind of hard to see here, is 1/3, then plus 1. So an exponent of 1/3 is the same thing as the cube root of x minus 5. Similarly, if I had a square root, I could write to the power of 1/2 instead. All right, now that I've graphed these two functions, I'm going to enter in the equation y equals x. Because if two functions are inverses, then they are a reflection across the y equals x line. And it sure looks like there is symmetry across the y equals x line here. So it's looking like these two functions are inverses. If we look at a handful of points a little more closely, here for the g function, we have the coordinate -2, -22. If I substitute -22 in here, then I should get out -2, and I sure did. Up here I have -1 comma -3. So when we substitute -3, we get -1, 0, 4 becomes 4, 0, 1, 5 becomes 5, 1, and 2, 6 becomes 6, 2. Notice that a comma b, a coordinate a comma b on g of x becomes b comma a on h of x. So at this point, it looks like h of x is a reflection of g of x across that y equals x line, which makes us think that yes, these are inverses. We checked out several points, a comma b on g of x, and we noticed that on the h function, those same points became b comma a. But what we've done here amounts to because it looks like it. We have a strong inclination that these two functions are inverses of each other, but we have not checked every single point that could possibly be on this function. And who knows, just looking at the graph, I think this crosses at 4, but how do I know it doesn't cross at 4.001? So now we're going to move on to a more formal approach at proving that g and h are both inverses of one another. Here's the more formal way of proving that two functions are inverses of each other. It's known as the inverse composition rule. A function f is one-to-one with inverse function g if and only if f composition g equals x for every x in the domain of g. G composition f of x is going to equal x also for every x in the domain of f. So if f composition g of x equals x, and also g composition f of x equals x. Now, really specifically back up there to emphasize that f function is one-to-one. So we're going to have f comp g is x, g comp f is x, and also we have to make sure that f is one-to-one. If all of that is true, then f and g are inverses of one another. Just to kind of explain this top half in layman's terms, if inverse functions, x's and y's are just swapping, So domain is x, range is y. So domain and range are swapping. Something that's really cool about inverse functions, we have a lot of rules to find the domain of a function, but not very many rules to find the range of a function. So you could write the equation of the inverse function, find the domain of the inverse function, and that is going to be the range of the original function. All right, let's go ahead and get to using this rule to prove that two functions are inverses of one another. Here we have those same two functions that we started with that we strongly suspect are inverses of one another. If we use the inverse composition rule, the first thing that we want to do is find G composition h of x and h composition g of x. So let's start with the first one. G composition h of x, we want to start with the g function. So notice x minus 1 cubed plus 5. Instead of x, I have that blank there. Composition h means every x in this g function is going to get replaced with the h function. So the x that used to be here is turning into the h function. Now I want to simplify. So as I begin to simplify, I see here that I have a plus 1 and a minus 1, so those cancel. And then I have the cube of the cube root of x minus 5. So if I cube this cube root, this will become x minus 5, and I'll still have plus 5. Simplifying further, minus 5 plus 5, those are gone, and we get just x. Woo! That's what we were hoping for. We want the answer to g comp h to equal x. Now we have to do this in both directions because g composition h is not necessarily equal to h composition g. We're hoping they are. If they both equal x, then we are one step closer to proving that these two are inverse functions. So let's find h comp g of x. Starting with the h function, and notice all I did here is I left the x out, and now I'm going to replace the x in the h function with the entire g function. So I'm going to put all of that right where the x used to be. Now that I've made that substitution, we want to simplify. Underneath the cube root, we have a plus 5 and a minus 5, and those are going to go away. And the cube root of x minus 1 to the third, that is going to be just x minus 1. So we have x minus 1, notice here, plus 1, and that equals x. The first part we have shown of the inverse composition rule, that g comp h equaled x and h comp g equals x. So do we now know for sure that g and h are inverses of one another? There's one other prerequisite that we have to make sure we have, and that is the g function, that function is 1-to-1. So remember, 1-to-1 means that this function passes both the vertical and horizontal line test. Another way to think of that is every x has a unique y, every y has a unique x. That's true. So since this g function is 1-to-1 and g comp h equaled x and h comp g equaled x, then by the inverse composition rule, we therefore, 3 little dots means therefore, g and h are inverses. So quick recap one more time. To use this rule, you begin by finding the composition both directions, in this case g comp h, then h comp g, and they should both equal x. If it does not equal x, then we already know that these are not inverse functions. Since they did both equal x, we had to go on just to verify that the g function was indeed 1-to-1. And since it's 1-to-1 and both the compositions equals x, we could declare that g and h are inverses of one another. Here we have two more functions, and we're going to attempt to algebraically show that g and h are both inverses of one another. So we're going to take g composition h. Notice I'm starting with the g function here, and instead of x, I have a set of parentheses, then plus 4, and instead of x, I have a set of parentheses, then minus 3. And then we're going to substitute in for where the x's used to be, we're going to put in the entire h function. All right, so there they are. Ooh, this is ugly. Remember, we are trying to simplify and make sure that this equals x. If you have a fraction within a fraction, the easiest way to simplify it is to first look for what I call the mini denominators. So my mini denominators here are x minus 4. So next you're going to put a set of parentheses around the bigger numerator and denominator, and you are going to multiply both of these by those mini denominators. And in this case, the common denominator is just x minus 4. I don't need to multiply by x minus 4 more than once. The goal is to get rid of these x minus 4s. Okay, so I'm going to multiply by distributing that x minus 4 through the numerator and through the denominator. But before I distribute, I'm going to go ahead and rewrite x minus 4 as x minus 4 over 1. It's just going to help you see this. So I'm rewriting the x minus 4s as x minus 4 over 1. And now I'm going to work on taking care of just the numerator. I'm going to distribute x minus 4 over 1 to each piece. All right, starting here, we want to multiply 2x plus 3 over x minus 4 by x minus 4 over 1. If you multiply these two fractions together, the x minus 4s cancel. And if they cancel, the only thing left when I multiply these two gray ones together is going to be the 2x plus 3. Okay, next, I'm going to distribute x minus 4 over 1 to the plus 4. When I multiply 4 times x minus 4 over 1, that's the same as 4 times x minus 4. So notice here, when I multiply it to the 4, I'm going to get plus 4 times x minus 4. All right, on to the denominator. I need to distribute this x minus 4 to each piece in the denominator. Let's start there. If I multiply 2x plus 3 over x minus 4 by x minus 4 over 1, this x minus 4 is going to cancel with that x minus 4, leaving me with just 2x plus 3. Then I'm going to distribute the x minus 4 over 1 to this negative 3. When I multiply those together, I'm going to have negative 3 times x minus 4 over 1. But that's really x minus 4 times the negative 3. Okay, so here we have that. See how much cleaner the numerator and denominator look now by just multiplying the top of this by x minus 4 and the bottom by x minus 4. Okay, now I'm ready to simplify the numerator and the denominators that I have. So if I distribute this 4 through, I get 4x minus 16. Distributing the negative 3, I have negative 3x plus 12. Let's go ahead and combine like terms in the numerator, making that 6x and minus 13, and then 2x and negative 3x is negative x, and 3 and 12 make 15. And the key here is what we have after we found g comp h, it's not x. So since g comp h does not equal x, we are done. We already know that these two functions are not inverses. We're going to go through this application of inverse functions. I'm kind of chuckling to myself because it says your wage is $8 per hour. Currently in Washington State, the minimum wage is $12 an hour, although in Florida State, it is only $8.46 an hour. It kind of dates myself because when I started working at 16, minimum wage was $3.85, which I was pretty happy about because it, I believe, had just gone up from $3.35. Oh my. All right, well, let's go with this number. Your wage is $8 per hour plus 75 cents for each unit produced per hour. Your hourly wage, Y, in terms of the number of units produced is Y equals 8 plus 0.75x. All right, let's just dig into that a little bit to make sure you understand the equation one more time. Let's say that you are making, I don't know, you are making a coaster. Well, that's exciting. And let's say you made 2 coasters in 1 hour. Well, then you get $8 plus 75 cents times 2 of them that you made, which is $1.50. So you would get $9.50 for that hour. If you did not produce any that in an hour, 75 cents times 0 plus 8 would be $8. So even if you didn't make any, you would still get $8 an hour. Okay, so now that we understand our variables, let's find the inverse. So to find the inverse, we want to take our x's and y's and just swap them. So this y is going to turn into x, and this x is going to turn into y. Now we want to solve the equation for y. Undoing the order of operations, I'm going to get rid of the add 8 before the multiply by 0.75. So I'm going to subtract 8 from both sides, and then I'm going to divide both sides by 0.75. This is technically our inverse equation, but it isn't really simplified considering we don't usually leave decimals in a fraction. So let's say I want to go above and beyond here and just get rid of that decimal in the denominator. You could do that a few ways. One way that I think would be pretty quick would be to multiply the numerator and denominator by 100, but then you might need to simplify. I'm just going to rewrite divide by 0.75 with a division symbol, and dividing by 75 over 100, that's the same thing as dividing by 3/4. Dividing by 3/4 is like multiplying by 4 over 3. So if I do multiply x minus 8 over 1 times 4 over 3, multiplying straight across, I end up getting 4x minus 32 over 3. All right, here we have our inverse function in simplified form, looking good here. Next, we want to explain what the variables in this inverse function, what do they mean? Well, let's look back at the original. In the original, the y was the hourly wage. Well, x's and y's just switched. So in the original, if the y was the hourly wage, well then now the x is the hourly wage. The y then would be the number of units produced because that was the x in the original function. Okay, so determine the number of units produced when your hourly wage is $22.25. We have a couple of options here to answer that question because we have 2 equations that we can choose from. We have the original equation and we have the inverse equation. This is going to help us to understand why would I have an inverse equation? Which one of these equations seems to be the easiest one to use? We know that the hourly wage is $22.25. In the first equation, we would be replacing the y with 22.25, but in the second equation, we would be replacing the x with 22.25. Notice I went ahead and just left it in the original form that I had, but we could have used the simplified version. Okay, so which one's going to be easier? I think the one on the right is a lot easier because y is already by itself. If I replace this y with 2225, now I have to solve an equation. So replace the x with 2225 and then subtract there in the numerator. 14.75 divided by 0.75 is 19 units. I want to mention one more little thing is, about simplifying equations. If I'm trying to answer the question, just this last part C, that's all I wanted to know. Well, then simplifying the equation might be just a bunch of extra work. If I'm wanting to have the inverse function, and that's my main purpose, well, then simplifying the equation would be important. Here's a classic example of inverse functions. I'm showing you this one to, again, just try to help you understand why would we have inverse functions. In the United States, since we use the Fahrenheit system, let's say that I am talking with a friend in England and they're like, what's the temperature out? And I say, oh, it is 70 degrees. Well, they wouldn't know about how hot that is. I would want to use the equation here on the right because I have Fahrenheit that I want to substitute in, and then I could take 5/9 times the Fahrenheit and subtract 32, and then I could tell them how much it was in Celsius. But if they were trying to tell me how hot it was outside, and they said, oh, it's about 15 degrees. I don't really know what that means. So they would likely use this equation here on the left because substituting Celsius is easier to do in this left one. 9/5 times 15 plus 32, and then they could tell me the temperature in Fahrenheit. So these two equations are exactly the same. They're the same relationship. It's just that one is solved for Fahrenheit and the other one is solved for Celsius. Before I conclude this lesson, I just want to bring up something that we've already covered. Here we have our 12 parent functions. Can you see if any of these functions appear to be inverses of one another? I'm not going to officially prove these ones to you using the F comp G and G comp F. We're just going to look at it graphically. You may want to pause for a second to see if you can tell which ones are inverses of each other before I reveal them. These two, y equals e to the x and y equals natural log of x, they're inverses of each other. Notice if I graph them on the same piece of graph paper, you can clearly see that one is a reflection of the other across the y equals x line. Here are two more that are kind of inverses of one another. If I graph them on the same piece of graph paper, notice that y equals the square root of x is almost the reflection across the y equals x line of y equals x squared. However, the parabola is too much graph. Often we limit the domain of one of the functions so that they are inverses of each other. So what we want to do here is we want to limit the domain of the f of x equals x squared. If we only keep the part of the parabola from 0, 0 to the right and leave off this left-hand side, well then y equals root x will be the inverse of y equals x squared. There we have it. By limiting the domain of f of x equals x squared to bracket 0 through infinity, x is greater than or equal to 0, now y equals x squared is the inverse of y equals root x. One last reminder for your homework assignment. You will have to build an equation in a story problem and they're going to give you the information essentially of two coordinates. Eventually, you'll find the inverse of the function that you build. But you're going to have to be able to remember how to write the equation of a line given 2 points. So the first thing you want to do is find the slope. And you use this equation here to use your two coordinates, subtract the y over x minus x, and you'll have your slope. Let's just pretend the answer to the slope is 8. And let's say your original coordinate was 2, 5. Then you would say y minus the y coordinate, which would be 5, equals 8 times x minus 2, because the 2 would be the x coordinate. You don't use both of the points. You have more information than you need at that time, because if you have 2 points and you have the slope to write the equation, you're only going to use the slope and one of the points. It won't matter which point you end up using. When you solve for y, you'll get the same thing.